pleased to introduce two speakers for this session, Peter Liu and Doğuş Akaydin. Peter is Vice President of Global Solutions Engineering and Customer Success at Rescale and is responsible for global technical pre-sales. He has over 10 years of experience in leadership roles at the intersection of HPC, cloud, and engineering simulations. He has bachelor's, master's, and PhD degrees in aerospace engineering from the University of Michigan, with an extensive background in computational fluid dynamics, multidisciplinary design optimization, and cloud architecture. Prior to joining Rescale, he led the CFD applications team at ComSol to help engineers accelerate innovation with multi-physics simulations. Doğuş is an engineering manager at Rescale, leading a team of engineers responsible for ML workflows and GPU-accelerated virtual desktop solutions. Before joining Rescale, he was a research scientist at NASA Ames Research Center for several years, contributing to the development of next-generation air and spacecraft. He has a PhD in mechanical engineering from the City University of New York and has postdoctoral training experience at Stanford University. It will now be our pleasure to hear from Peter Liu and Doğuş Akaydin.
Hello, everyone. Thank you for joining Big Compute 2022 and the session on AI for engineering and design. I want to start by asking you to imagine the toughest engineering and scientific challenge you have ever seen. Imagine a process that takes months or years for engineers and scientists to work through those challenges. Would it be amazing if we can somehow automate this problem-solving process? My name is Peter Liu. I lead our solution engineering and custom sets team at Rescale. And I'm very excited to talk about AI engineering and design together with my colleague Doğuş. When I was doing my PhD study many years ago in aerospace, I had one of those challenges. I want to automate the design and optimization of an aircraft. What if we can start with a sphere and tell the computer algorithm that we want to turn that sphere into an aircraft design, say carry 500 passengers comfortably and efficiently across the pond from New York to London, and let the algorithm go to work. Now, obviously, we didn't succeed it, since there isn't an aircraft today flying in the sky that is designed by AI. But we was able to achieve this automation in a limited fashion. So if we can have a carefully designed algorithm and simulation and lots of computation power, we're able to automate a subset of designs, such as optimization of the wing and the shape of the wing, and external of the aerodynamic of the aircraft. For example, we can turn a sphere by putting an optimization algorithm on top and a few constraint and objective, and turn that sphere into an airfoil, as you can see here. Now, that's far from able to design an aircraft from end to end, but it shows the potential. So, why is it so difficult to achieve this? Today, why designing a complex engineering system, such as a commercial aircraft, that it actually involves tens of thousands of engineers and for years to be able to come up with the design and achieve the objective? There's two factors leading to that. Now, number one, the algorithm is just not smart enough. What I mean is that if you have a well-defined problem with the objective and well-formulated constraints and boundary conditions, yes, the computer algorithm has proven to do very, very well. It can come up with some optimum design within that design space, and it can actually often come up with designs that is much better than something can be come up by human and come up by engineers. Now, in a real-world situation, it's often very, very hard to come up with a very, very well-formulated problem and come up with a design space. In a real-world situation, you may have millions of different constraints, and even just missing one of them, that may lead to a useless design. So we need an algorithm that not only can explore this design space, but maybe they're even able to come up with this design space or come up with the problem itself. And that's where artificial intelligence and machine learning algorithm come to the picture. Now we have lots of advancement in this area in the last decade. More recently, applied AI to engineering designs. And we have seen many of our partners and customers start to develop specialized AI ML algorithms and software tailored for their engineering simulations. And we've seen also our cloud provider partners to really develop some of the infrastructure layer to make it much easy to apply any of the AI ML algorithms running on the cloud infrastructure. Now, while we're not there yet, that we're able to turn a sphere into a commercial aircraft design, but we've seen that AI-assisted engineering now start being applied in the industry. And you may hear some of those examples from our partner presentations today. Now, the number two reason is the sheer amount of computation power needed to solve those problems, and solving them at a scale that never seen and never done before. So with the advancement of cloud computing technology, those type of elastic or burst computational resource now become more accessible. Particular GPUs, where now you can use hundreds, if not thousands of GPUs to run those large-scale training. And so then engineers and scientists now able to actually really leverage that and combining the different AI ML algorithms to tackle those problems today. At Rescale, we aim to help combine all those factors together. And we've seen many of our customers able to come up with those algorithms themselves, but many customers may not have the skill set and knowledge to be able to piece the AI ML algorithms, the simulation tool, and the underlying infrastructure together. So our goal is to be able to combine the CAE simulations, such as finite element, computation fluid dynamics, and those software provided by many of our partners, the AI ML frameworks and algorithms that is available today, and the underlying infrastructure from many of our cloud provider partners to make it very easy to use and to combine that into a single platform to support our customers to be able to do AI-assisted simulations and AI-assisted design exploration. And we're excited to share with you some of the examples that we're able to work together with our partners and customers to really explore this area and to see what is possible to achieve in this discipline. Now with that, let me pass on to my colleague Doğuş, who's going to share with you a little bit more detailed examples of some of the recent examples that we've done with our customers.
Hello, my name is Doğuş Akaydin. I lead some of the components of Rescale's AI for R&D program. The AI for R&D program aims to enable AI/ML capabilities on Rescale. We are interested in these because these capabilities can help accelerate engineering discovery and design processes by orders of magnitude. Let me explain in more detail what we mean by AI for R&D. If we take a design of a mechanical system as an example, a typical process would look like this cycle. It starts with the pre-processing step, which includes notoriously labor-intensive processes such as CAD cleanup, defeaturing, and mesh generation. This step is followed by a compute-intensive step for simulating the response of this model under various conditions, and it typically produces a large amount of output data. In the post-processing step, this data is summarized and visualized by generating images, videos, as well as field and tabular data for further processing. Finally, all the data produced thus far is used to develop databases to help engineers decide what to do next. Go back to drawing board for further improvements or ship the design for prototyping. Unfortunately, all of these steps are bottlenecked by various limitations in computational resources or human capabilities. For example, the CFD Vision 2030 study led by NASA in 2014 recommends certain areas of focus to overcome a number of challenges identified in the CFD workflows. These areas of focus include geometry and grid generation, optimization, porting codes to new CFD hardware, visualization, and novel numerical algorithms. And since 2014, a lot has happened in the intersection of HPC and AI, making once academic or even non-existent capabilities to start readily making impact on production workflows in various industries. So by AI for R&D, we mean automating this engineering design cycle and its subcomponents as much as possible by taking advantage of these new technologies on Rescale platform. With this vision, we went on to developing example workflows relevant to some of our customers. For example, this ML-driven optimization workflow trains a surrogate model to rapidly design airfoils. This workflow not only produces a surrogate model for the end user, but it also uses a partially trained surrogate model to accelerate its own training process. You can take a look at this tutorial to learn more about this workflow. Building the previous example helped us identify some of the gaps we have in the technical capabilities and expertise. As described in the diagram, building an AI-powered workflow at scale on cloud requires well-abstracted and scalable application layer and hardware infrastructure layer. So supporting the AI box on top would be exceedingly complex if we were to build all the capabilities from ground up. So instead of aiming to build all these capabilities by ourselves, we build partnerships with other players in the ecosystem to integrate with their technologies and expertise. And two, we build core functionalities and interfaces needed to enable these integrations at scale. Now, let's take a look at some of the examples of these integrations. The first example is our integration with AI-powered simulation technology of neural concept, an ML framework called NC Shape that enables users to develop surrogate models using simulation data. With these surrogate models, the engineers can estimate the impact of a design change much faster than they could by running a new simulation. For example, here it takes only 15 milliseconds, near real time, for NC Shape to come up with a reasonable prediction, whereas getting the same answer from an equivalent CFD simulation would take about 2 hours. Furthermore, these surrogate models can be used in conjunction with pre- and post-processing tools to predict and visualize the impact of these changes practically in real time. This gives the design engineers the ability to rapidly iterate over the changes they would make without having to regenerate CFD-ready CAD geometry and computational grid. The machine learning engineers interact with the framework over a Jupyter Notebook-based GUI to manage the simulations and data and to build and train the machine learning models. Then, the design engineers access these models to develop the product by running design studies and creating visualizations and reports. The partnership is beneficial to all parties involved, including the customer, because running NC Shape on Rescale makes the deployment and maintenance of these workflows much more scalable and more flexible. In addition to neural concept, we have a major partnership effort going on with NVIDIA, which spans across the whole stack of NVIDIA AI software and hardware. NVIDIA is not only the leading AI chip designer, but it also is a major developer of AI and graphics software. Similar to HPC hardware and software by other providers, Rescale is very well positioned to bridge these applications with the hardware at scale across multiple CSPs. On the hardware front, Rescale is able to utilize NVIDIA GPUs on all major and some special cloud service providers. We are also in the process of integrating with NVIDIA Base Command, which will provide Rescale users to further access to DGX systems that they may own on their on-premises systems, or they may utilize on NVIDIA-owned data centers. At the application and frameworks layer, we have integrations at various levels of maturity. Some have recently went into production, such as the support for NVIDIA Modulus and NVIDIA NGC containers, and some others, such as NVIDIA Omniverse, is only at the roadmap level. Today, Rescale users can pull containers directly from NGC repository maintained by NVIDIA. Many of these containers are optimized and tested by NVIDIA to run on different lines and generations of their hardware, removing that burden from the shoulders of the end users and IT staff. Modulus, the cutting-edge physics ML tool that we will talk about next, is also available on Rescale today. As an NVIDIA partner, Rescale engineers work with NVIDIA engineers to ensure that Modulus runs optimally on multiple multi-node GPU instances across various cloud providers. Finally, we are hoping to add Omniverse on Rescale to further extend the AI/ML capabilities to real-time collaboration for inference and graphics rendering. As I mentioned earlier, Modulus is the state-of-the-art physics simulation framework that relies on deep learning techniques to model physical phenomena. In the interest of time, I will just summarize why Modulus is a game-changing tool that you should learn about. Modulus relies on deep learning using data that can be dynamically generated as part of the training process, or using external input coming from other simulation tools or even test strings. Because it is effectively a deep learning approach based on neural nets, it runs efficiently on GPU hardware by design. It obviates the need for mesh generation because it operates on point clouds rather than computational meshes. Similar to adjoint methods, it can compute multiple derivatives of field variables, which is a feature very relevant to multidisciplinary optimization. And Modulus is starting to being used in real-life applications, notably by Siemens, NVIDIA, Argonne National Labs, Berkeley Labs, and more, on problems such as heat sink design, wind farm optimization, weather forecasting, and plasma physics simulation. On Rescale platform, you can run Modulus on various sizes and kinds of NVIDIA hardware to scale it up or out to your specific needs. For example, in this case, we collaborated with Kinetic Vision to scale out their Modulus training. In this project, Kinetic Vision was aiming to build a surrogate model into a SolidWorks CAD environment for rapidly prototyping an air blade nozzle. The Kinetic Vision engineer prototyped and tested their Modulus setup on their on-premises workstation, which had 8 NVIDIA V100 cards. We took this work and then scaled it out to train on 64 NVIDIA V100 cards across 8 nodes on a cloud provider. Finally, we ran the same workflow on A100 cards to compare the cost and performance. We found out that NVIDIA A100 cards are twice faster, running the same training load, and they can also be 10 to 30% cheaper, depending on the cloud provider pricing you use. So being able to run Modulus on Rescale would allow the customers to effortlessly test different NVIDIA hardware, explore different pricing options available to them across different cloud providers, and ultimately scale out their workflows up to the timeline and budget requirements. As you can see here, on Rescale platform, Modulus is only a few clicks away from you. All you will need to do is to pick Modulus from the software menu, and then pick the hardware you want to work with, select the number of nodes to scale out, and number of hours you want to run this job for, and add your input files. You can add from your local platform, local code, local workstation, or you can add from the cloud provider, cloud storage. And define a project for tracking the budget and submit the job. If it's a batch job, it will automatically start automatically running using the commands you specify. If it's a virtual workstation, it will come to life within several minutes with all the dependencies you wanted to see on the desktop environment. In this case, I'm fast forwarding to previously created desktop environment with training already going on. As you can see, you can get a GUI environment with training going on multiple nodes. And there are also a variety of tools that you can install onto this workstation to visualize the progress of your training session. So now that the model is trained, it can be made usable by for design engineers and other people downstream of the work. So and NVIDIA Omniverse in this case will be the natural extension to achieve this. With Omniverse, people from different teams can collaborate on the design process. The machine learning and simulation engineer would enable the trained model for example, the mechanical design engineer to run a rapid design study. And then the graphics designer could then render beautiful images and videos of the proposed design, all through a remote collaboration session within Omniverse. As I mentioned, Omniverse is not yet available on Rescale, but it's on our roadmap to further with NVIDIA. I would like to circle back now to depict how these technologies can help overcome the challenges identified in the CFD Vision 2030 study. As you can see, a change in a foundational approach to simulating physics opened up the way to remove many of the barriers in the way. In this example, we focus on the NVIDIA modulus, but we can similarly make similar connections to other AI or GPU accelerated is coming from our partners and ISVs we work with. As part of this engineering and partnership activities, we have developed a number of resources to onboard users. One of these is a free trial program where we offer several hours of compute on select NVIDIA hardware through Rescale platform. We would like to invite you to take advantage of this program to try for yourself the capabilities we just mentioned. And we look forward to speaking with you further to build AI-powered engineering on Rescale. Thank you very much.